Thank you, Pablo. I welcome you all on this afternoon, the last day of the Vision Fair, and I have good news for all who like it fast. So if you have inspection with a very fast speed, then maybe this is interesting for you. Yeah, here's a quick outline. I want to talk about the problem, then a bit of comparison between line and scan and area scan, then the technology that the solution that we as AIT propose. Then always, when being very fast, light is an issue, and also, yeah, I talk about the FPGA design we did inside the camera to achieve this, and at the end I go to possible application fields and benefits you get with this solution. The problem is there are some processes in industry where you have really fast moving parts or fast moving objects you want to scan, and there normally for fast inspection you use line scan cameras, but also today's line camera technology has a limit around 600 kilohertz or a bit more now, as I have seen. So we thought what we could do. An example is, one example would be rail inspection, so inspection of the surface of rails. Rails are very narrow structures, but you have to go very fast. Or another very impressive example is wire inspection. So for hot wire, speeds between 100 and 150 meters per second. So this is around 400 kilometers per hour, really fast. Is an issue, and when you want to scan at this speed with 600 kilohertz, you get a resolution about 0.2 millimeters, which is not very high because wires are normally very thin. So very thin and very fast is normally a bad combination for normal cameras. And the solution idea is now we profit a bit from the development of area scan cameras. Area scan cameras are a bit further in terms of lines per second they can achieve. We use an area scan camera, but on the output, on the interface to the PC, we make it look like a line scan camera. And with this we can the basic idea is to have a special camera with a sensor that has a 0 frame overhead time, so we can read out the sensor at about 100,000 times per second. So we have order of 100 kilo frames per second, but only a region of interest of 10 sensor lines. So 10 times 100,000 is the million I'm talking about. Yeah, and but the normal issue is that normally those sensors, those fast sensors, have this frame overhead time. So a time that you have to wait between 2 frames because of the internal of the sensor. So it's necessary to have a very special sensor. This is not possible with every sensor, of course, and some sensors have poor performance in image quality if you have run them with too high frame rates. But we have a viable solution here, a viable combination. We have found an off-the-shelf camera, so the camera hardware is not from us. We buy it with it approximately 2K times 1K area image sensor with a very high frame rate. Full sensor can be read out at 2,200 frames per second. This sensor has, as I mentioned, 0 frame overhead time, so it becomes fast if you read out order of 10 lines. And last but not least, the FPGA can also be extended by the customer. Normally, the vendors of cameras don't like that the customers program something inside the camera. In this case, this is possible. And with this, we can also handle some artifacts from the sensor directly in the digital domain in the FPGA. And so we realized a scanner, now it's the question if it's an area scanner or a line scanner, but at the output it's a line scanner with 1 megahertz line rate. Now here's the principle. The principle I explained for a field of view of 4 lines. So we read out from the sensor 4 lines, and we make in fast sequence the images of those stripes of 4 lines. And if we stitch together those blocks of few lines, then we get an image of, let's say, 1,000 lines, which is can be well processed by the PC afterwards. So at the output, it's an area image of order of 1,000 lines, but from the sensor is triggered in the order of 100,000 lines per second. And that's the reason why we talk about a virtual line rate, because sensor side is triggered order of 100,000 times per second, but only at the output, the result is equivalent to a line scan camera of 1 megahertz. Yeah, maybe, I hope you see it. This comes from our first tests. This can happen if you have inhomogeneous illumination. Then you see here some gradient in the brightness. These are stitching artifacts you don't like, of course, but they come from inhomogeneous illumination, and if you have too many lines per block. So it's necessary to reduce the number of lines, and then this effect vanishes. Now, how to illuminate. Also, illumination is not so easy, because 1 megahertz line rate means 1 microsecond exposure time, and there we use the benefit of modern LED technology, because modern LEDs can be strobed very fast. Also, the white LEDs can be strobed with pulse durations in order of 1 microsecond or even below, and that we make short pulses of 1 microsecond and then several microseconds where the LED has time to cool. So this is also called overdrive, and this leads to the effect that we can have during the light pulse. Here is the 1 microsecond light pulse. We can have a really highly intensive lighting with high intensity, which is much higher than if you would turn on the light the whole time for continuous lighting, because in the time between the pulses the LEDs can cool down. Yeah, and then altogether this area scan camera, which is now on the output a line scan camera, together with this fast illumination, of course we have to synchronize very well the camera and the illumination. Oh, something happened. Then you see here the example of the surface of a banknote, a 10 euro banknote, with somebody interferes here. We can, at 10 meters per second, we can resolve this tiny micro writing on the banknote. Do I have to hurry? Is the time gone? Yeah. So you can I can show you this in the demo. The effect is that you see this this tiny writing, only 0.2 millimeters high, even at 10 meter per second. Yeah. One word to the FPGA design. The camera we used has an infrastructure that the green box, this is the complete FPGA, it can be programmed by the user. Of course, the user must have skills about FPGA programming, so Vivado tools and VHDL or Verilog. The infrastructure looks in this way, that there is an IP block, 2 IP blocks from the vendor of the camera. You can't change, and you have to live with all signals that come out and go into these gray blocks. This is the vendor IP for the sensor control and for the interface. But in between, you can have your own, you can design your own FPGA processing. You can do fine things of very fast image processing inside the FPGA. And in this custom IP, we realized this fast stitching. And also the triggering. Also, you have also trigger signals, the trigger signals available, so we also realized the synchronization with the illumination. So, yes, this is, we used high-level synthesis in our design, so the high-level synthesis result looks like this. Here you see a floor plan of the complete FPGA. You see it's 2/3 are already used now, but there's still room for further algorithms inside. Yeah, and here, this is what the demo looks like on the right side. Sorry, this was me. Yeah, we have the benefit, as you see, is you have a camera resulting with 1 megahertz line rate, and you can use an off-the-shelf camera to realize it. Yeah, the application fields are in high-quality metal inspection, wires and cable. Sorry. Can it be stopped also? I don't know. Inspection of infrastructure like rail or road surface, print inspection, also color is possible. Then inspection of battery electrodes you can combine it also with photometric stereo, as you see it here, and PCB inspection and many other where speed is important. So I come now to the end. With this talk, I conclude that we demonstrate here the ability to scan with 1 megahertz line rate or even more, and this is enabled by fast area scan technology available on the market, and also fast LED strobing technology, and hopefully there's much benefit for the industries who need that speed. Thank you.